Welcome to SS2 Physics, Term 3, Week 8. In 1905, Albert Einstein published his special theory of relativity, one of the most revolutionary ideas in the history of science. It showed that our intuitive ideas about space and time are only approximately correct, and that at very high speeds, close to the speed of light, space and time behave in completely unexpected ways. By the end of this lesson, you will state the two postulates of special relativity, understand the concept of time dilation and length contraction, apply the mass-energy equivalence E equals mc squared, and answer WAEC-type questions on special relativity. Let us begin. Before 1905, physicists believed in absolute space and absolute time, that measurements of distance and time are the same for all observers, regardless of their motion. Einstein's special theory of relativity overturned this. Two postulates of special relativity. Postulate 1, the principle of relativity. The laws of physics are the same in all inertial, non-accelerating, reference frames. There is no experiment you can do inside a closed box that can tell you whether you are at rest or moving at constant velocity. Postulate 2, constancy of the speed of light. The speed of light in a vacuum, c equals 3 times 10 meter per second, is the same for all observers, regardless of the motion of the source or the observer. This second postulate is extremely counterintuitive. If you are on a train moving at 100 km per hour and throw a ball at 50 km per hour forward, a stationary observer sees the ball at 150 km per hour. But if you shine a torch forward from the same train, the stationary observer measures the light traveling at exactly c, not c plus 100 km per hour. This is the experimentally confirmed result, Michelson-Morley experiment, 1887. The implications of these two postulates are profound and strange. They lead to time dilation and length contraction. Time dilation: a moving clock runs slower than a stationary clock. Time passes more slowly for a moving observer relative to a stationary observer. Mathematical expression: T equals T0 slash square root 1, V superscript 2 slash C superscript 2 equals T0 times gamma, or Lorentz factor gamma equals 1 slash square root 1, V superscript 2 slash C superscript 2, where T equals time measured by stationary observer, dilated time, T0 equals proper time, time measured by the moving observer's own clock, always the shorter time, V equals velocity of the moving observer, C equals speed of light. The Lorentz factor gamma is always greater than or equal to 1. At low speeds, V much less than C gamma is almost equal to 1, no significant time dilation, everyday experience. At V equals 0.866 C, gamma equals 2 to 1 second for the moving observer equals 2 seconds for the stationary observer. At Vc, gamma infinity, time slows to a stop for the moving observer relative to the stationary one. Example: muon time dilation. Cosmic ray muons created in the upper atmosphere at V equals 0.998 C have a rest lifetime of 2.2 microseconds. In the Earth's frame, their lifetime is dilated by gamma equals 1 slash square root 1, 0.998 superscript 2, is almost equal to 15.8. Dilated lifetime is equal to 15.8 by 2.2 microseconds is almost equal to 35 microseconds, long enough to reach the Earth's surface. Without time dilation, muons should decay long before reaching the ground, but they are detected at sea level. This is direct experimental evidence for time dilation. Length contraction: a moving object is measured to be shorter, in the direction of motion, than when at rest. L equals L0 times square root 1, V superscript 2 slash C superscript 2, equals L0 slash gamma, where L equals measured length, shorter, L0 equals proper length, rest length, gamma equals Lorentz factor. Lengths perpendicular to the direction of motion are not contracted, only the dimension parallel to V. Perhaps the most famous equation in physics, E equals mc squared. This arises from special relativity. Rest energy: a stationary object with rest mass m0 has a rest energy E0 equals m0 c superscript 2. Even a small mass corresponds to an enormous amount of energy. Example: 1g equals 0.001 kilograms of matter has rest energy E0 equals 0.001 times 3 times 10 superscript 2 equals 0.001 times 9 times 10 superscript 1 equals 9 times 10 superscript 1 superscript 3 j equals 90 tj, enough to power a city for a day. Total energy of a moving object, E equals gamma m0 c superscript 2 equals m0 c superscript 2 slash square root 1 v superscript 2 slash c superscript 2. At low speeds, this reduces to E is almost equal to m0 c superscript 2 plus 1/2 m0 v superscript 2, rest energy plus kinetic energy. Relativistic mass, concept as velocity increases, an object's resistance to further acceleration, relativistic mass, increases. At Vc, it takes infinite force to accelerate further, hence no object with mass can reach c. Relativistic momentum, P equals gamma m0 v equals m0 v slash square root 1 v superscript 2 slash c superscript 2. Evidence for E equals mc squared. Nuclear reactions, fission and fusion, mass is converted to energy. The measured mass of products is always less than mass of reactants by exactly the amount predicted by E equals mc squared. PET, positron emission tomography, scanners, positrons from radioactive decay annihilate with electrons, positron plus electron 2 gamma photons, the mass of positron plus electron pure energy in the form of gamma rays, E equals m_e plus m_e, times c superscript 2 equals 2 times 9.11 times 10 to 31 times 9 times 10 superscript 1 equals 1.64 times 10 to 13 j equals 1.02 MeV, split between 2 gamma photons of 0.51 MeV each. WAEC questions on special relativity at SS2 level are typically conceptual and calculation-based at the introductory level. Common question types: state the two postulates of special relativity. Explain time dilation with an example. Calculate the Lorentz factor for a given velocity. Apply E equals mc squared to calculate energy from mass defect. Compare classical or Newtonian and relativistic predictions for velocity and energy. Worked example: a rocket travels at 0.6 c. Calculate A. the Lorentz factor, B. if the journey takes 5 years in the rocket's frame, how long does it take from Earth's frame? A. Gamma equals 1 slash square root 1 v superscript 2 slash c superscript 2 equals 1 slash square root 1 to 0.36 equals 1 slash square root 0.64 equals 1 divided by 0.8 is equal to 1.25. B. T equals gamma times T0 is equal to 1.25 times 5 equals 6.25 years. Common misconceptions: time dilation does not mean time stops for the moving observer, it still passes normally for them, it is the relative comparison that gives dilation. Relativity does not mean everything is relative in a philosophical sense, the laws of physics are the same for everyone, that is the first postulate. The speed of light is absolute and constant, it is not relative. Relativity is confirmed by GPS satellites, which must account for both special and general relativistic time dilation to maintain accuracy. Particle accelerators, particles must be treated relativistically, atomic clocks on aeroplanes. Key points: 2 postulates. 1. Laws of physics same in all inertial frames. 2. Speed of light constant for all observers. Time dilation: moving clocks run slow. T equals gamma T0, where gamma equals Lorentz factor equals 1 slash square root 1 v superscript 2 slash c superscript 2 greater than or equal to 1. Length contraction: moving objects are shorter in direction of motion. L equals L0 slash gamma E equals mc squared. Rest energy of mass m0 is m0 c superscript 2. Mass and energy are interchangeable. Experimental evidence: muon time dilation, nuclear mass defect, positron-electron annihilation, GPS corrections. Key values: C equals 3 times 10 meter per second, gamma equals 1 at V equals 0, increases without limit as Vc. Nothing with mass can reach or exceed C. WAEC on relativity, state postulates, explain/calculate time dilation, E equals mc squared calculations, qualitative discussion of length contraction.